Okay, in this video I'm going to go over some theorems for polynomials that I'll be using in subsequent videos that I'll be doing. Let's look at the first one. It's a remainder theorem. Let f be a polynomial function. If f of x is divided by x minus k, the remainder is f of k. So we're just looking at an example. Let's consider, say, x squared minus 4 divided by x minus 2. So in this case, the f of x over here in the statement of the theorem is x squared minus 4, and the x minus k is represented by x minus 2. So if I wanted to divide this and only find out what the remainder was, I could do a long division and figure it out. Or if I use this theorem, in this case the k would be 2. So this tells me to find the remainder, I replace the x by 2 in the polynomial function. So put a 2 where the x is 2 squared is 4, minus 4 is 0. So the remainder would be 0. So that also tells me that x minus 2 is a factor, because when I divide x minus 2 into x squared minus 4, I get remainder 0, so x minus 2 is a factor. Now, the factor theorem follows directly from the remainder theorem. So the factor theorem states, let f be a polynomial function, then x minus k is a factor of f of x, if and only if f of k is equal to 0. Okay. So in the previous example, x minus 2 is a factor of x squared minus 4 because f of 2 is 0. Notice if I replace the x by negative 2, I replace the x by negative 2, negative 2 squared is 4, 4 minus 4 is 0. So x minus a minus 2, so you have to put it in the form x minus k, is x plus 2. So that would tell me that x plus 2 then is also a factor. Okay, so that's one way you can determine if a particular binomial is a factor of another binomial or a trinomial. You could use long division, or you can just apply the remainder theorem. Okay, the next one, the rational zeros theorem states, let f be a polynomial of degree 1 or higher of the form. Okay, so we have the standard form written in descending powers. We want the lead coefficient over here not to be 0, and we want the constant term, a sub 0, not to be 0, and where each coefficient is an integer. So it states, if p over q, okay, that would be a rational number, so it'll be something like 1/2 or 1/5 or negative 1/2 and so forth, in lowest terms is a rational 0 of f, then p must be a factor of the constant term, that's the a sub 0, and q must be a factor of the lead term. Now I want to point out to you that if it turns out that the constant term is 0 here, a sub 0, and so the last term has an x, you could still apply the theorem, but you'd have to factor the x. Then this term here, say a1, would be your constant term, and then the theorem would apply. So if we look at this example right here, x squared minus 4, that's your polynomial, so consider x squared minus 4. In this case, the constant term, or the lead term, is 1, and the constant term is negative 4. So according to the theorem, if you wanted to find the possible rational zeros, you would take the factors of the constant term, find those, and those would be factors of negative 4 would be plus or minus 1, plus or minus 2, plus or minus 4, and the factors of the lead term would be plus or minus 1. So basically you divide each of those factors into the factors of the constant term, and you would get plus or minus 1, plus or minus 2, plus or minus 4. So according to the rational zeros theorem, the only possible rational zeros that x squared minus 4 can have would be either plus or minus 1, plus or minus 2, or plus or minus 4. And of course, as we have just seen, the actual zeros are 2 and negative 2, because those are the numbers that make x squared minus 4 0. Okay. Now, Descartes' rule of signs allows you to find the possible number of positive real zeros of a particular polynomial, or the possible number of negative real zeros. So here's what it says. The number of positive real zeros of f either equals the number of variations in sign of the non-zero coefficients of f of x, or else equals that number less an even number. Okay, b, the number of negative real zeros of f either equals the number of variations in sign of the non-zero coefficients of f of minus x, or else equals that number less an even number. Okay, now the polynomial does have to be in the standard form, so that's in descending powers. So if we were to look at this example here, so if I wanted to look at, say, x squared minus 4, very basic polynomial, and want to know, okay, what are the possible positive real zeros of this polynomial? I would look at the variation in sign. Okay, so it goes, anytime it goes from plus to minus or minus to plus, it's a change in sign, okay, or variation. So here goes such plus, and then it goes to negative. So there's one variation. So that tells me I would expect one positive real zero. Now, to find the possible number of negative real zeros, you evaluate this at negative x. So put a negative x where the x is. Well, because you have the square, it doesn't change. It stays the same, x squared minus 4. So the number of variations is still going to be 1. So in this particular one, I would expect, in this polynomial, I would expect one positive real zero and one negative real zero. And that's what we have. Okay? The conjugate pairs theorem tells me let f of x be a polynomial whose coefficients are real. Now the key to this theorem is that the coefficients have to be real numbers. Okay, so they can't be imaginary numbers like an I or a 2i and so forth. So this one tells me if r is equal to a plus bi is a zero of the polynomial f, then it must be true that the conjugate, which is a minus bi, is also a zero of f. And I'll illustrate this in the overview that I'm going to do now. Okay, so if I were to consider the polynomial, the one I just looked at, okay, so let's look at the polynomial x squared minus 4, and it factors into x minus 2 and x plus 2. So obviously from that we can get the zeros and we can get the factors. Okay, so now with the possible rational zeros, using the rational zeros theorem, the possible rational zeros are going to be factors of negative 4, which are plus or minus 1, plus or minus 2, plus or minus 4, divided by factors of the constant term. Okay, it is a 1, so that's plus or minus 1. So if I divide the factors of minus 4 by the factors of 1, I get the same thing. Because all I'm doing is dividing by 1 and negative 1. So I get possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4. Now we know that the actual zeros are 2 and negative 2, so we get one positive and one negative. Okay, because I have a factored form there, you can see the zeros. Okay, now I just went over this number of variations in sign. So if I look at the polynomial x squared minus 4, number of variations is just 1. So I would expect, as I said before, one positive real zero. Okay, if I replace the x by minus x, again because of the square it stays the same, so the number of variations in sign of f of minus x is still 1. So I would expect one negative real zero. And like I said, these are just possibilities. Okay, so in this case then I get 2 and negative 2, so one positive and one negative. Now, getting back to the theorem, okay, the number of positive real zeros of f of x either equals the number of variations in sign of the non-zero coefficients of f of x, or else equals that number less an even number. So here's what you're going to do if you're working something like this. Here's a little chart. So if the number of variations in sign for either f of x or f of minus x, okay, so remember when you look at the signs, variations in sign of f of x if you're looking for the positive real zeros. And you look at the variations in sign of f of minus x if you're looking for the possible negative real zeros. So if you have 0 variations, okay, you expect 0, okay? So if there's no variations in sign, then there's no positive zeros and no negative zeros. Now you could have imaginary zeros, but again, imaginary numbers do not have a sign associated with them. So if I have a negative I or a plus I, those are not real numbers. So we only associate a negative or a positive number with real numbers. Okay. Now if you have one variation in sign, then you're either going to have one positive real zero if you're looking at the signs for f of x, or one negative if you're looking at the signs for f of minus x. And it continues if you're looking for, if you have two variations in sign. Okay, so here's where the this part goes into play. Or else equals that number less an even number. So basically what you're going to do is subtract 2. From the number of variations that you have, you subtract 2. And notice, 0 subtract 2 gives me a negative 2. So I can't have a negative 2 number of variations, okay, because I'm counting the number of variations, so I have to have a positive or 0. 1 minus 2 is negative, so that doesn't make sense. Okay, now here it's 2, subtract 2, so here it's 2 or 0. So you have two variations in sign. You either have 2 or 0, positive or negative depending on what you're looking at. If you have 3 variations in sign, subtract 2, we get 1, so it's 3 or 1. Okay, 3 or 1, positive or negative, depending on whether you're looking at f of x or f of minus x, the variation in signs. If you have 4 variations in sign, it will be 4, 2, or 0. If you have 5 variations in sign, then again, 5 subtract 2 is 3, subtract 2 is 1, subtract 2 again, you get a negative, so you stop there. So for 5 variations, the number of possible either real or negative or positive real zeros could be 5, 3, or 1. Okay, and those are possibilities. Okay, you don't know which of these is going to be true until you go through and solve for the actual zeros. Now, if this comes out 0 here, then that's the answer. Okay, 1, that's the answer because there's only one option. But these have several options, so the only way you're going to know for sure is to actually solve for the zeros. So as another example, let's look at the polynomial f of x equal x squared plus 4 instead of x squared minus 4. Okay. Now in this case, notice I have again a 1 and a 4. So if I want to know what are the possible rational zeros, then I would have, okay, factors of 4 again, plus or minus 1, plus or minus 2, plus or minus 4. Factors of 1 would be plus or minus 1. So if I do the division, then the possible rational zeros are going to be either plus or minus 1, plus or minus 2, or plus or minus 4. Now in this case, we don't have any rational zeros, okay? Because we just, those are just the possibilities. If you have rational zeros, it's going to be either plus or minus 1, plus or minus 2, plus or minus 4. In this particular case, we have no real zeros at all, okay? Now, let's look at the variations in sign. Okay, well, notice positive and positive. So 0 variations. Okay, so that's this one. 0, 0. Notice if I replace the x by minus x squared is x squared. So again, I have 0 variations. So what does that tell me then? Well, it tells me it has 0 variations in sign for f of x and for f of minus x. Thus, it has no positive real zeros and no negative real zeros. However, it does have imaginary zeros, okay? Because if you take x squared plus 4, set it equal to 0, okay? So let's do this. If I want to know, okay, when is x squared plus 4 equal to 0? Well, put the 4 on the other side. Got to make it negative 4. And then take the square root. And then plus or minus the square root, okay. Plus or minus the square root of 4, that would be 2. Plus or minus 2I, okay, because it's negative 4. So x is equal to plus or minus 2y, so that's why this is. However, it has imaginary zeros of 2I and minus 2y. Okay, so this is just a brief explanation of theorems. I'll go into more detail in the next video when I work problems again in more detail that involve some of these theorems. So again, stay tuned for the next video, and please subscribe if these are helping you, and we'll see you next time.